Hello. My talk today will be taking you through a full design automation flow for superconducting electronics. My name is Jamil Kawa, and this work was done with Rick Borges and Bob Freeman, both colleagues of mine at Synopsys. First, I'd like to start with an acknowledgement of the Office of the Director of National Intelligence Advanced Research Projects, IARPA, for supporting this project throughout. The areas I'll be covering are the classical design flow for design automation, starting with synthesis through GDS2, but also some front-end tools starting with TCAD all the way through design kits, SPICE models, and so on, essentially a PDK. And I'll show you how we did all that with an example based on the famous AMD 2901 4-bit slice microcontroller. So first, what was the challenge? Superconducting electronics has many families. Most common of them are the 5 you see below: RSFQ, ERSFQ, DSFQ, RQL, and AQFP. We were given the challenge by IARPA to automate the design of at least 2 of those families and achieve it through 1 million gates or 10 million Josephson junctions with an ARC processor or RISC processor, 64-bit, etc., at 100 gigahertz. By the way, the basic device of the superconducting electronics that we are dealing with is the Josephson junction, presented here with the cross sign in all the sample circuits you see below. Of those families, we embarked on RSFQ, ERSFQ, and on AQFP. However, for the 2901, AMD 2901 example that I will go through, we focused on ERSFQ, which stands for Efficient Rapid Single Flux Quantum. So what did we do? Exactly, we leveraged our experience in CMOS and started with a classical CMOS flow, starting with specification, high-level design, RTL coding, functional verification, synthesis, place and route through fabrication, and post-silicon validation. So that's where the similarities end for superconducting electronics. However, for the ERSFQ example, or for superconducting in general, there are many variants that make them unique. Starting with the following. The Josephson junction is a 2-terminal device. It has no voltage gain, and for most applications or for most families, fan in equal fan out equal to 1. What does that mean? It means there is a special circuit called splitter that you will need every time you need to branch a signal to 2 or more inputs. Also, the fluxtron, which is the basic element of signal for this technology, loops in an infinite loop inside a quantizing loop. Therefore, all gates are clocked gates except for splitters. Another variation that is unique to superconducting electronics is power delivery. Unlike VDD and VSS rails, here power is delivered in the form of very high currents at very low voltages, and that's a big challenge for realization. Also, the interconnect is not your classical wire with high impedance that is usually used in CMOS. The interconnect is either a JTL or a PTL. JTL being Josephson transmission line, or PTL passive transmission line. And each of those have their own particular uniqueness to deal with when you are doing a back-end flow. For this design automation, we are doing using a PTL passive transmission line, which is really a lossless transmission line, impedance equals 0. Therefore, the signal travels at roughly between half and 1/3 the speed of light. And you need driver and receiver for that with every cell, which we incorporate. Also, similar to what we did in CMOS, we're embarking on a flow based on DTCO for superconducting, more of that in the coming slides. So what is our approach? Superconducting electronics in terms of automation is in its infancy. So superconducting electronics could use its own so-called Moore's law. So for that, we need robust tools that address all aspects of the technology, starting with the technology itself, the technology development, and then the design enablement, and finally realization automated design. So in this slide, we give you a presentation of the technology development itself. We have TCAD tools and we have design enhancement tools or layout enhancement tools. For the TCAD tools, we do physics-based mathematical analysis of Josephson junction for modeling, starting with the materials and layout, and we integrate that with OPC procedures for making sure the layout reflects all the additional changes made for manufacturability. And based on that, we generate SPICE models. In between, there is a tool that I'll be talking about in the next slide. But the idea is that the next thing is the design enablement in the form of creating a PDK design kit that allows us to do either custom design or standard cell designs for final full synthesis and automation. So focusing on the DTCO and the technology development, we are starting here in the upper left with Josephson junction structure, the TCAD simulation, which again is based on basic physics mathematical equations, generate models for the behavior of the Josephson junction across temperature, across all variables related to the material, to the thickness of the junction, and so on. And those data sets are fed for a tool called Mystic that is an intermediary tool between TCAD and SPICE. Now, Mystic has two features. It can take noisy data from wafer runs and smooth them out to create SPICE models, or it can start with data from TCAD. The important thing to stress about Mystic is it is not a best fitter curve. It's a tool that will take the data and makes the best curve that will capture the major behavior of the Josephson junction, the kinks that differentiate the main behavior, such as critical current, such as when does it go normal, and so on. So output of that would be a SPICE model, which is necessary for the next step, which is superconducting electronics PDK, process design kit, which will include a technology file, the run sets for DRC and LVS, very similar to what you're familiar with in CMOS, the ITF file needed for star RC extraction, and the SPICE models. So with that design kit, you can do the basic design of standard cells, as well as if you want to do a custom circuit design. So you start with the tool called Custom Compiler that interacts with IC Validator that can also call on star RC, which is an extraction tool. And you start with basic cell layout or circuit netlist, and you use the HSPICE models generated to do some simulations. All these HSPICE simulations, you need to verify the logic of the basic elements or of your custom circuits. And based on that, you end up with a .lib, a library of standard cells, which you will use for the backend. Here, of course, I'm ignoring that for custom designs, that by itself is a step that will take you all the way. So essentially, the DTCO flow supports scaling of superconducting electronic technologies to achieve higher functionality. Also, although we're doing all this flow work and front-end work for superconducting electronics, we have an eye for providing the same set of solutions for quantum computing superconducting designs, especially for qubits using superconducting qubits, especially for quantum computing. So back to focus on the custom design flow. For a custom design flow, whether your end is a full circuit or is a set of standard cells that will become a large library, you start with a technology file describing the design rules, describing the layers, describing the whole stack of the process. And you have run sets for design rule check, DRC, and LVS, layout versus schematic run set. You have the intermediate file that has data for fitting for extraction of capacitance, inductance, and resistance. Of course, you have the SPICE models that is either based on heuristic data from wafers fit through the tools, or based on TCAD mathematically or physics-based models. The tool for the front-end capturing is Custom Compiler, as I mentioned. It interacts from within Custom Compiler. It's a layout and schematic entry tool, but interact dynamically with IC Validator, which is an engine for running DRC and LVS. It can also call on StarRC for extracting. It can also interact with HSpice. The idea is in Custom Compiler, you can have a schematic-driven layout. You can validate the functionality and the cleanliness of the layout. And out of that, you get a circuit netlist for simulation, as well as a clean cell layout. You do extract the resulting design or the resulting cell in StarRC. In StarRC, at the level of the cell, you need very accurate inductance extraction. So the StarRC at this stage uses field solvers, mainly based on fast Henry, to extract inductances very accurately. You back annotate the parasitics to your netlist, run HSpice, and you have circuit simulation output. Of course, if you're doing that for a whole set of libraries, you do cell characterization and you end up with a standard cell library with the .lib format. The .lib format rhymes with the .lib format of the CMOS, but it has its own entries because the timing in this case is a little different to characterize and to tabulate than a typical CMOS with its corners. Custom Compiler. Custom Compiler is the workhorse tool that we use for front end. And as I mentioned in the previous slide, it starts with a technology file that captures all the features of the technology. It includes run sets for DRC and LVS. It includes data file for extraction and SPICE models. It interacts with HSpice, with StarRC, and most importantly with the LVS DRC run sets and the engine to end up generating a clean library entry or a clean custom design. Some of the features I want to stress out of Custom Compiler are all listed to the right and below. So you have device connectivity checking, you have cross-probing between schematics and layout, you have schematics-driven layout, which is a very efficient feature, and then you have layout connectivity, which is easy to trace and probe layout continuity of functionality. The next step is you want to validate that what you have captured is correct between schematics and layout. You want to validate that the layout reflects what you captured in schematics in exactly the same manner that you do in CMOS, and that's the function of the IC validator. Here, everything is very similar in terms of schematic versus layout that you're familiar with in CMOS, with one minor exception, that inductance extraction is very tricky because unlike capacitance, which is really contained in terms of next door neighbors, inductance is a long range feature, and many inductors are covers multi-layer interaction, so you need accurate extraction for that, and you need quite intricate field solver behavior, and the way in which you do the meshing and the realization is pretty important. So then the next is StarRC. StarRC is the extraction engine. StarRC is extremely important. Here, unlike CMOS, all your wires are really pure inductors. At the temperature at which we operate, which is 4 degrees Kelvin, all the wires are pure inductors. And therefore, when you are doing inductance extraction, there are two levels of complexity for inductance extraction. At the level of a single structure or at the level of a small cell, you need absolute accuracy, and that's where you use field solvers. Most famous of them is Fast Henry. A lot of our field solver extraction for inductance is based on Fast Henry with our own modifications and variations. But the other one that's equally important is chip level extraction. You're not going to use field solvers for a chip level. It will take days, if not weeks. Therefore, you need to come up with models based on lookup table, but also you cannot afford to lose accuracy. So we do all kinds of design structures to validate what we are doing in terms of lookup table. Also within StarRC, we have the ability on localized region to call for more accurate field solvers to improve the accuracy depending on what we are doing. HSPICE is, of course, the same HSPICE that we've used for CMOS, but modified for superconducting electronics. For superconducting electronics, capacity is important. This is an example of the curve of voltage versus current, and you can see the critical current, you can see the linear region, you can see the gap area. So as I was mentioning earlier, it's not important to do a best fit for the curve for HSPICE as much as to capture the key junctions that distinguish superconducting Josephson junction behavior from other behavior. So we currently have a Josephson junction temperature dependent model, RSJ. We support Monte Carlo simulation and variability analysis. We have an extensive set of regression suites, and with validated circuits with greater than 100,000 Josephson junction devices. Now, let's go to the 2901 place and route that I mentioned at the very beginning of the talk, which is what we use to establish a methodology for our back end, starting with synthesis all the way through a chip finishing. Again, I want to stress that we decided to go with a methodology of using PTL, passive transmission lines, for our interconnect. What does that mean? It means that for all our standard cells, we've equipped each standard cells with a PTL transmitter and a PTL receiver. That isolates the timing of the cells from each other. That makes timing accountability extremely easy and makes automation much easier and possible. Another thing I want to mention from the very earlier slide, when I mentioned that in superconducting electronics and the ERSFQ family, every single element, with the exception of splitters, is really a clocked element. Therefore, the clock tree synthesis is extremely difficult in terms of having equalization. So what did we do for clock tree synthesis? We started with an H3 structure using, of course, from the center, using splitters. So the splitters will make sure that each endpoint, similar to here that I am hovering over, are all equalized in the delay. And for each end, you have a few sync points locally that are also managed very nicely to equalize the delay of the clocks. That's extremely important. There are many methods of clocking. For this particular example, we use that clocking method, and I won't focus on other ones for the time being. For routing, we are partnering with our partner Hypress for standard cell libraries that have tracks of metal 2 and metal 3 orthogonal within each cell that are allocated for PTL routing. M0 is left for power routing, and we've allowed for channels in between the rows to allow for additional routing to avoid. This is the routed 2901 block. You see end cap cells. We ended up powering all the rows at the level of metal 0 through a continuous track of metal 0 for power. So that meant we need to put filler cells to make sure for the continuity of the M0 line. Also, filler cells allow us to have additional tracks in the vertical and horizontal direction as well in terms of continuity. One thing, a quick note, a quick look at this diagram shows you as if the ratio of filler cells is huge. There is a reason for that, being we only used the very basic minimum size filler cell. We did not create larger filler cells, so the statistics are a little skewed. This is the finished product, the routed 2901 with its statistics. I can see I am running out of time. So again, back to conclusions. Superconducting electronics is embarking on its own Moore's law. We are using a DTCO strategy to enable superconducting the same way we enabled CMOS and advanced scaling. Arriving at VLSI for superconducting is going to be very challenging, so we have to have a strategy. Some of the challenges are associated with power delivery. The narrow pulse arrival window makes timing extremely challenging. lack of memory solutions, and the concept of flex trapping. I don't have time to go through these, but I'm giving you here a flavor of what we are focusing on. And with that, I want to thank your attention.